last video lecture, we discussed the mission instructions and addressing modes. The topic instruction pipelining, finding the execution time or number of clocks. Okay, so simply a program will be given. Then in the instruction pipelining concept, so how many number of clock cycles it will take to execute that program, or finding the execution time. Right? So both concept and previous gate problems will solve on this concept. Instruction pipelining, this is the only concept here. Try to clearly understand the concept first, then from after completing this concept, let us go to solve the previous problems. Let us assume there is for the CPU, 5 stages are there, 5 units, right? Fetch the instruction, decode the instruction, and operation, execution, computation, and to write the result, finding the effective address, okay, to store the result and write into the memory or register. So these 5 units, you assume a CPU consists of these 5 units. Suppose if there is no pipelining concept, okay, so this is the instruction 1. To execute this instruction 1, right, if j equal to assume 1, instruction 1, then it will take how many clock cycles to execute the instruction 1? 5 clock cycles. Okay, 5 instruction 1 plus instruction 2, again it has to fetch, decode, compute, memory, and write the operation 5. For instruction 3, then it will take once again 5 clock cycle. Assume that each stage will take 1 clock cycle. Then if there is no pipeline concept, total how many? 15 clock cycles it will take to execute the given program. This is non-pipeline. Okay, and if you assume there is a pipelining concept, okay, where each unit separately it will execute, where each unit will operate individually, then to execute these 3 instructions, how many clock cycles it will take? Let us see. So at the fetch unit, okay, the instruction I1 will be entered at the first clock cycle, okay, and the second clock cycle, this whatever the fetched instruction will be given to decode stage. So I1 is now decoding in this second clock cycle. At this time, right, at this time decode is busy, but fetch unit is ideal, okay, because the previous I1 already given to decode stage. Then at this time the fetch unit is free, so that's why next instruction is, let us say, I2 entered. See here at the clock cycle 2, what happening? Decode unit is decoding the instruction I1, and fetch unit is fetching the instruction I2. Okay, now at clock cycle 3, what happens? Let us see. This I1 is already decoded, that is given to execution unit. This is I1 is computing the operation, or execution we can call it as. That time decode unit is free, so that's why whatever the fetch I2 is given to decode unit, because this is free. And already this instruction I2 is fetched. Now fetch unit at this time the fetch unit is free, that's why next I3 is entered in the fetch unit. So at a clock cycle 3, what is going on? Computation unit is computing instruction I1, decode unit is decoding instruction I2, and fetch unit is fetching the instruction I3. At the same time, these 3 units are busy. Now after completing this, at clock cycle 4, at time T4, let us say, at this time what is going on? This computed already clock cycle 3, I1 is computed, that is given to memory stage. Okay, this time compute is free, that's why this I2 is given here, this I3 is decoded. Now at clock cycle 5, again these 3 are busy. This I1 is given to writing the result operation. Okay, this I2 is given to this memory unit, and I3 is given to computation execution. That means at T5, what is going on? I1 is writing the results, and I2 instruction is finding the effective address of the memory, and at the same time I3 is execution unit. Okay, so if you observe at a clock cycle 5, I1 is completed. Then at clock cycle 6, what is going on? This water I1 is completed, and I2 reach to the right, because this right operation is free, that's why I2 is written here, and uh, I3 is given to the finding the effective address unit. Okay, at this time at clock cycle 6, this I2 is completed. Okay, now at clock cycle 7, what is going on? These two already completed, and this I3 is given to the right unit, and this is also completed here. So that means if you observe this one at clock cycle 5, I1 is completed, at clock cycle 6, I2 is completed, at clock cycle 7, I3 is completed. Okay, that means if suppose I4 is there, then next clock cycle 8, it is completed. That means for every clock cycle, one instruction is coming out. Okay, so that is the difference between non-pipeline and pipeline. Right. Previously it is non-pipeline, 5 plus 5 plus 5, total 15 clock cycles is taken, but here you see 7 clock cycle it is executed. Okay, so pipeline speeds up the processing. For example, if there are 3 instructions, assume each instruction has to go through 5 stages to compute its execution, and each instruction will take 1 clock cycle, you assume. In non-pipeline processor, the time taken to execute 3 instruction 3 into 5, because every instruction 5 stages, there is no pipeline, so that's why 15 clocks it has to take. In pipeline processor, the time taken to execute 3 instruction equal to, we need to remember this formula, right? How 7 clocks will arrive? N plus k minus 1. N is number of instructions, k is number of stages, right? Minus 1. See here how many instructions are there? 3. K is number of stages, how many? 5 stages are there, minus 1, that is 7 clocks. For example, there are 100 instructions. Okay, in non-pipeline processor, the time taken to execute 100 instruction equal to 100 into 5. Why? Every instruction has to go through 5 stages, because there is no pipelining. 100 into 5, that is 500 clocks. Whereas in pipeline processor, the time taken to execute 100 instruction equal to, what is the formula? N plus k minus 1. N plus k minus 1. What is N? Number of instructions 100, k is the number of stages 5, minus 1, that equal to 104 clocks. Okay, see here comparison. In non-pipeline it is 500 clock cycles, in pipeline that is 104 clocks. This pipeline concept increases the speed. Okay, here k is the number of pipeline stages, and n is the number of instructions. So this is the pipeline execution in the ideal case. So in this concept, let us solve some problems, right? Previous gate problems. So where they will give some number of instructions now to find out the number of clock cycles to execute that program. Let us go to the practice problems. So this question is asked in gate 2007 for 2 marks. Consider a pipeline processor with the following 4 stages: instruction fetch and instruction decode or operand fetch. Both are combined. Sometimes they will give OF. OF means operand fetch. Here ID stage, both instruction decode and operand fetch is given, and execution stage and a write back stage. Write the results into the memory. So these 4 stages given here. Okay. Assume each stage will take 1 clock cycle to complete the operation. But whereas he has given for execution stage depends upon the instruction. This IF, ID, WV will take any instruction 1 clock cycle. Right? But whereas execution stage he has given that for add and subtraction 1 clock cycle, for multiplication that is 3 clock cycles it will take. That means 2 extra clock cycles in the execution stage. So this information is given, and one more information is operand forwarding is used in the pipeline processor. What is the number of clock cycles taken to complete the following sequence of instructions? Number of clock cycles to execute this program. Okay, option A 7, option C 10, option B 8, option D 14. So you are advised to pause the video and try on your own. After completing, getting the answer, whatever it may be, any answer, but check your answer by running the video, right? So that you will get full concept. So let us solve this problem. 3 instructions are given, that is add R2, R1, R0. This is a 3 address instruction. And second instruction is mul R4, R3, R2. And third instruction is sub R6, R5, R4. Okay. Here if you observe these 3, what is the meaning of the first instruction? R1 plus R0, the result is stored in R2. Mul instruction R3 into R2, the result is stored in R4. And subtraction R5 minus R4, the result is stored in R6. So if you observe, after execution of the result, this R2 need to take this one. After execution only the result R2 is available, then only it can able to execute this second operation. This is data dependency. Okay, the instruction I2 depends upon the instruction I1, because after executing then only R2 value is available, the result, and that value need to take this one. These 2 instructions are dependent. In the same way, if you observe I2 and I3, after executing this R4 you will get, then R4 is the one of the operand we need to take here. So these I2 and I3 also data dependent. Clock cycle 1, what happens? There are 4 stages. The instruction 1 is entered into this IF stage, right? And clock cycle 2, what happens? This IF is given to ID stage, and at this time IF is free, that's why I2 entered, this multiplication entered into IF stage, because this is free. Now at clock cycle 3, because each will take, he has given each will take only 1 clock cycle, right? This I1 add instruction is entered to execution stage, and at the same time this ID unit is free, that's why this multiplication instruction entered to ID stage, and at the same time IF is free, so that's why subtraction instruction is entered to this IF stage. That means at clock cycle 3 what is going on? The add instruction is executing in the execution stage, multiplication is decoding here in the decoding stage, and subtraction instruction is fetching the instruction from the memory in the IF stage. clock cycle 4, what happens? Because the add instruction already completed execution unit, then the result is storing back in this. That means this R1 plus R2 is completed, that is stored in R2 here. Okay. At the same time, the execution is free, that's why the multiplication instruction already entered in the execution stage. At the same time, this ID is free, so that's why subtraction after fetching this, subtraction instruction is entered to decoding stage. Now add instruction already completed here at the 4th clock cycle. Okay, at the 5th clock cycle, what is going on? Then this execution unit, the multiplication instruction, it will take, he has given 3 clock cycles to execute. So that's why it will continue the execution of the multiplication instruction at the 5th clock cycle as well as 6th clock cycle. Here operand forwarding concept will come. See here, R2 is available after writing back. Okay, that means this execution unit, if there is no operand forwarding, it has to start from here. It has to start from 5th clock cycle, because after completing this, it has to start here EX, EX and EX. But because the operand forwarding technique is there, this when it is writing, then this operands will be writing here in the 4th clock cycle, that is given to the execution stage directly. No need to wait to up to completing the WB write back unit to be completed. Directly the data is available after execution, that is directly taken WB to execution unit of next multiply instruction, because R2 is available here directly. This is called operand forwarding. If there is no operand forwarding, it has to start execution in here and here and here. Okay, because after completing the 4th clock cycle, it has to start the execution unit, because it has to wait for R2. But because the concept in the hardware there is operand forwarding, this when writing the WB, no need to complete the 4th clock cycle, directly the R2 will be taken directly to the execution unit to execute the multiply instruction. Okay, so that is called operand forwarding. Right. So multiplication execution will take 3 clock cycle, and if you compare at the 5th clock cycle, okay, the subtraction instruction is decoded over, but this will not start the execution because the execution unit is already busy, because it is taking 3 clock cycle, so that's why it has to wait these two clock cycle. After completing execution unit, then at the 7th clock cycle it is writing back the result. At the same time, because operand forwarding is there, directly the value of R4 is given to execution unit. Now execution unit is free and the data is also available here at the 7th clock cycle, that is taken directly to the execution unit. Then this multiplication is completed here, and the next clock cycle, because subtraction, it will take only 1 clock cycle to execute, then at the 8th clock cycle it is written back, right back into the result R6. Okay, so that it will take only 8 clock cycles. Option B is correct. Let me tell you the conclusion. So actually operand forwarding technique, okay, so here after completing this, R2 is available at the 5th clock cycle, then execution should start here, EX, EX and EX. But because of the operand forwarding, when it is writing, it is also there is a path to the execution unit, then it can start here only, EX, EX and EX. That is operand forwarding technique. Okay, why this is stalled here? Then execution unit is busy. After completing the execution unit one instruction, then only the next clock the next instruction will be executed. So these are the basic concepts, right? So answer here is B option is correct. Consider the sequence of machine instructions given below: multi instruction, division instruction, add instruction, subtraction instruction. 4 instructions he has given. In the above sequence, R0 to R8 registers are there. In the instructions shown, the first register stores the result of the operation performed on the second and the third register. In the instructions shown, the first register stores the result. See here, this first register stores the result of the operation performed on the second and third registers. Second and third register, that means R0 plus R1, the result stored in the first register. Here also R2 divided by R3, the result is stored in R6, like that. This sequence of instructions is to be executed in a pipeline instruction processor of the 4 stages. How many stages here given? 4 stages. One is IF, second is OF, operand fetch, and perform operation execution unit PO, and write back the result. The IF, OF, WB stages take 1 clock cycle each for any instruction, but the PO stage takes 1 clock cycle for add and subtract, 3 clock cycle for multiplication, and 5 clock cycle for division instruction. The pipeline processor uses operand forwarding from, see here, PO stage to OF stage. Directly it will take. That means after the PO, that is the execution unit, perform the operation. PO means perform the operation. That means execution unit to directly OF. The last stage of PO stage, directly we can take the data. There is a path to OF stage. That is called, that means no need to wait after completion of the PO. Directly from the last stage, you can take the data to operand fetch. Now the question is the number of clock cycles taken for the execution of the above sequence of instruction is. See here, there are 4 instructions are given: multiplication, division, add, subtract. Okay. At first clock cycle, what is happening? The multiplication instruction entered to IF stage, right? At the second clock cycle, because it will take only 1 clock, at the second clock cycle, this multiplication instruction to entered into the OF stage, that is operand fetch stage. At the same time, IF is free, that's why division instruction already entered. At the same time, next instruction entered to IF stage. At the clock cycle 3, okay, this multiplication instruction already entered to the executing stage, perform operation. At the same time, OF operand fetch is free, so that's why division instruction is whatever the operands are fetched here. At the same time, the IF is free, that's why add instruction entered to the pipeline. Right. At fourth clock cycle, what happening? Because multiplication instruction, how many clock cycle it will take? See here, 3 clock cycles for multiply instruction, that is PO, perform operation stage. That's why PO, once again this PO will continue. But if you see at the 4th clock cycle, this perform operation of division will not start because the PO is already busy, so it has to wait. And here add instruction, the OF we should not start because the operands, because there is a data dependency here. After execution of this, only this R6 add instruction will be available, so that's why it is ideal. Okay, after the PO operation, then operand forwarding is there, that time only we need to start operand fetch. Operands are available. Okay, so that's why it has to wait. Then at the same time, the subtraction instruction if is free, that's why it enters if stage. That is the fourth clock cycle. And see, in the fifth clock cycle, right, the multiply instruction will take three clock cycle to execute the perform operation. So that's why the PO continues here. And then division instruction, PO is busy, it has to wait. And add instruction, because it has to wait for the operands, that's why it is idle. And then here also R7, it is data dependency, it has to wait until the PO completes, then that's why it is idle. Because all these instructions are data dependency. See here, mul and division, there is no data dependency, but R6 it has to wait, and here R7 it has to wait. Okay, and see I3, that means add instruction has to wait for this R5 also. Right? There is a data dependency. This add instruction depends upon multiply and division instructions, and subtraction instruction depends upon add instruction. Right? This is the fifth clock cycle. At sixth clock cycle, what happens? PO multiplication is completed. PO1, PO2, PO3. So 3 clock cycles completed, and it is the result is right back R5. At the same time, since PO is completed, because there is no data dependency multiplication and division, directly this division instruction, the perform operation will be started, because this is free here. Okay, but add instruction, okay, this operand fetch, it has to wait, because until the PO operation execution, this R6 we need, right? Until the PO operation, it has to wait. And here also there is a data dependency, it has to wait until the PO operation, right? Now at clock cycle 7, what happens? This multiplication already completed, and the division instruction, it will take see here, division instruction 5 clock cycles for division instruction, the PO stage. That's why PO, 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 and PO, PO up to here. Until PO, this OF stage should not start, because it is a data is available at the PO stage after the PO. Because see here, the operand forwarding PO stage to OF stage. This is called operand forwarding. So clock cycle 8, clock cycle 9, clock cycle 10, it has to wait. And this also has to wait until the PO operation of add instruction, it has to wait. At clock cycle 10, what is happening? Let us see. PO of our division instruction is completed here. Then no need to wait up to 11th clock cycle, because of the data forwarding concept is there. Directly this is available. The data is available directly. There is a operand forwarding technique. So while the PO completed, then directly see here, the PO stage to OF stage, there is a operand forwarding technique. That means this R6 value is available directly here only. Directly it is forwarded to OF stage also, operand fetch. Okay. If there is no operand forwarding, this OF stage has to start here. But because of operand forwarding technique, PO to OF, then directly this R6 will be taken here only. That is called operand forwarding technique. Okay. Now it has to wait, because the PO operation will not be done here. Add instruction is in OF stage only, so it has to wait here. That's why there is a stall here. Now at the 11th clock cycle, what is happening? This PO is completed, division operation is completed, then it is right back. Then add instruction PO will start here, because operand fetch is completed and PO stage is free. Then the execution of the add instruction will be start, because operands are already available. Then pivot stage is free, then it can start. At the same time, at clock cycle 11, subtraction operand fetch will starts here because there is a data operand forwarding technique from PO stage to OF stage. Directly the result R7 will be taken. Result R7 will be taken. No need to wait up to 12 because of operand forwarding PO to OF. The whatever the result R7 will be taken. Operand fetch is done here at the same clock cycle. That is the advantage of operand forwarding PO to OF stage. The 12th clock cycle, this add instruction is completed because for the PO operation it will take only one clock cycle, add and subtract. So here write back will be done and the PO stage is free. Now subtraction will be executed here in the perform operation stage, and then at 13th clock cycle this result R8 will be written here in the result. The result will be written into R8 register. So total how many clock cycle? It is 13 clock cycles. Okay, is the correct answer. One more thing here, there is a PO to OF. Okay, that means if you see the first two instructions, it has to no need to wait up to the last stage of PO. OF directly it can start here because these two are not dependency. The hardware will check whether if there is a dependent, because see here there is a dependent, that's why it has to wait up to PO to OF. See here there is a data dependency here between add and subtract, that's why it has to wait last PO instruction, then take the operand forwarding. Okay, but here this OF, okay, no need to write because these two are not dependent. Okay, that is a operand forwarding technique. Here there are 5 stage pipeline processor is given: IF, ID, the instruction decode, OF operand fetch, perform operation, execution stage, and WO write operand. Okay, 5 stages are given. Okay, and the information is given is IF, ID, OF, and WO will take 1 clock cycle for each for any instruction, but the PO stage 1 clock cycle for add and subtract, and 3 clock cycles for multiply, and 6 clock cycles for division. Some change is there in this problem compared to previous problem. 6 clock cycles for division instruction respectively. Now operand forwarding is used in the pipeline. Operand forwarding is also there. That means whenever the data available, there is a path to get to the next clock at the same time. Now, what is the number of clock cycles needed to execute the following sequence of instructions? I0, I1, I2, I3. Multiplication, division, add, subtract. Okay. Now, option A 13, option B is 15, option C 17, option D 19 clock cycles. Now, use the same concept. What is operand forwarding? In this technique, the value of operand is given to the concerned stage of dependent instruction before it is stored. That means no need to wait until store operation, right? Directly it is forwarded. So here if you observe these 4 instructions, what are the instructions are dependent? Okay, here see I2, observe I2 is dependent upon this I1 instruction, and this also depend upon this I2. Until completion of this I0, I1, then only okay this operation will be done. And if you see I3, there is also dependent, the result R2 will be taken to this. I2 is dependent upon these 2 instructions, I3 dependent upon this I2. Yeah. Here operand forwarding, that means after the completion of PO stage, then operand fetch will be taken. This is the operand forward as previous. Okay. Right. At clock cycle 1, what happens? This multiplication instruction entered to IF stage, At clock cycle 2, and the instruction multiplication instruction will be entered to instruction decode stage. At the same time, this instruction fetch unit is free, that's why this division instruction already entered. Okay, at clock cycle 3, this operand fetch, okay, operand fetch of the multiplication instruction will be done. At the same time, the instruction division instruction will be entered to, because id is free now, instruction decode, that is I1 next instruction will be decoded here. At the same time, this if is free, that's why add instruction entered, fetched here in this stage. The clock cycle 4, what happens? This multiplication instruction entered to PO stage, and OF is free, so stage is free, operand fetch stage is free, that's why division instruction entered to OF stage. And instruction decode is free, at the same time add instruction is entered to ID stage. And IF is free, that's why subtraction instruction already entered in the same clock cycle 4 IF stage. Next clock cycle, what happens? The PO stays continuous, because the multiplication instruction will take 3 clock cycles to execute the PO operation, that's why PO stays continuous. But at the same time, this PO of the division instruction will not start, because PO is already busy, so there is a stall here. Here also add instruction, okay, OF will not start, because there is a data is required after completion of division instruction, then it is R5 and R2, okay, R5 should available after end of the PO stage, then only operand fetch will be done, so that's why it is stalled. And here ID subtraction enter ID, because it is free. At clock cycle 6, the instruction multiplication instruction will start continue, because it will take 3 clock cycle for the PO operation. Now it is completed, and since PO is not completed here, this is stall here, and it has to wait for the operands, it is both are stall. Now at clock cycle 7, what happens? The PO operation of instruction multiplication is completed, then it is writing operation, writing the operands. So now at the same time, clock cycle 7, the PO is free. Now multiplication is completed, then division instruction entered to the PO stage, and then it continues to third PO, fourth PO, fifth clock cycle, and 6 clock cycles it will take to execute the PO operation of division instruction he has given. So until that, this add instruction, the OF will not be started here, and subtraction OF will not started here, operand fetch operands are not available. So at the clock cycle 12, what happens? The PO completed, but no need to wait up to 13 for the data available. There is a operand forwarding technique, PO to OF directly it is taken the data, this, or directly you can write like this, right? See here, operand forwarding, computed value of R3 by R4 is forwarded from here at the same clock cycle, that is called operand forwarding, okay. Then this OF will not start, because the PO stage of add instruction will not be completed, that's why there is a stall here, right? Now if you observe clock cycle 13, what is going on? This PO the perform operation of division instruction completed after 6 POs, then it is write the result, write the operands, okay. Now at clock cycle 13, division instruction also completed. Now at the same time, the add instruction, if you observe, now PO stage is free, already division instruction completed, now operand fetch is over, then PO stage it enters. and add instruction will take only one clock cycle for PO. At the same time, because PO has been completed here, at the same time, because operand forwarding technique is there, that's why there is a directly taken to OF. Let me see here, R2 directly taken at the PO stage. PO to OF, there is a forwarding technique. Then at clock cycle 14, okay, the perform operation of add instruction completed, then it enters to write the operands, and the PO stage is free and operand fetch is also over, then the subtraction instruction entered to PO stage. 15th clock cycle, this subtraction instruction also entered to WO stage. Now it is completed. So total 15 clock cycles are needed, hence option B is correct. What is the conclusion? We remember, so if there is a data dependency, then from PO up to PO it has to wait and then take the data directly. No need to wait after PO. 13th clock say no need to wait because of operand forwarding, directly it is taken to OF stage. And here also there is a data dependency of the I3 and I2, then this directly after end of the PO directly it is taken. There is a path here, hardware is such that PO to OF directly the data is taken. One may ask a question, sir, it is executing at the PO, how the data until it is end, it has to wait, how it will takes, because the clock cycle is like this clock cycle, right? Suppose if it is completed, this is one clock cycle, right? One clock cycle up to here, at the first half it is completed and the next half it is forwarded just. So that's why at the same I written. So this is operand forwarding, right? Total 15 clock cycles are required. Very easy. Now this question is asked in GATE 2009 for 2 marks. Okay. Consider a 4-stage pipeline processor. 4 stages are there and 4 instructions are there. 4 stages are S1, S2, S3, S4 like this. These are the instructions. These are the instructions and these are the 4 stages S1, S2, S3, S4. The names not given, but you assume and that is a instruction fetch, decode, execute and write back the operation. So in the table as given for S1 stage it will take I1 will take 2 clock cycle and remaining 1 clock cycle. For I2 S1 will take 1 clock cycle, remaining 3, 2, 2 clock cycles. Okay, and I3 S1 takes 2 clock cycle, 1, 1 and S4 stage will take 3 clock cycle. Like that some information is given. Okay, what is the number of cycles needed to execute the following loop? I equal to 1 to 2, that means first iteration and second iteration also it has to do. For I1, I2, I3, I4, these 4 stages has to go through 2 iterations, then how many clock cycles are needed? This information is given and we need to run 2 I1, I2, I3, I4 and I1, I2, I3, I4. At the first clock cycle what is happening? S1 stage is entered. Instruction I1 S1 stage it takes 2 clock cycles, that's why S1 S1. Okay, until this S1 will not start, I2 instruction will not enter to stage S1 because S1 is busy at the clock cycle 2. At clock cycle 3, now S1 is completed, I1 entered to S1 2 clock cycles and S1 is completed, so that's why it enters S2 and S1 is free, I2 enters into S1 at the same clock cycle 3. At clock cycle 4 what happens? S2 it is only takes 1, that's why S2 completed and I1 enters to S3 stage. At the same time this I2 only 1 clock cycle S1 is completed, then it enters to S3 3 clock cycles. Okay, S2 and S2. and at clock cycle 5, right, this S3 completed, because this is 1 only, and S4 is also 1, so this is completed at clock cycle 5. Okay, and here at clock cycle 4 only this I3 enters S1 because it is free. Okay, now it takes 2 clock cycles, so S1 and S1, because I4 will not enter to S1 because this is busy here, this is stalled here. Okay, now at clock cycle 5 I1 is completed, then clock cycle 6 what happens, this it is continuing S2 because it is S2 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 3, it is now completed. Because this S2 is busy, then there is a stall here, it should not start even though S1 is completed, it should not enter into S2 because S2 is already busy. Now at clock cycle 6 S1 is free, that's why it can enter in clock cycle 6, I4 is entered in S1 stage. Now okay, at clock cycle 7 what happens, this S2 of I2 is completed, now it enters to S3. See here, S2 is completed and it enters S3, 2 clock cycle, S3 and S3. So this time at the clock cycle 7, so S2 is free, that's why I3 enters here. And because of S2 is busy, then there is a stall here, I4 will not enter into S2. And then here S1 is free, then next iteration starts. Okay, next iteration starts, then I1 enters. Because S1 is free, okay, then next iteration starts, I1 enters. At clock cycle 8 what happens, this S3 is completed now, and because of S3, even though S2 is completed of I3, then there is a stall here because S3 is already busy, it should not start S3. Now here I4 will enter into S2 because S2 is already empty, S2 is free, that's why it enters to this one. And I1 will generally take 2 clock cycle according to given data, so it continues S1 and S1. At clock cycle 9, right, here see here I2 S3 completed, and there are two clock cycle take for S4, so S4 enters, and I3 enters into S3 because S3 is free because already is over. Now I4 continues to next stage also because I4 will take 2 clock cycles. This is already over, 2 clock cycles. So S2 continues. Now because of S2 is busy, S1 I1 once again it should not enter, so it has to wait. Now here S1 is free, so that's why I2 in the second iteration enters here. At clock cycle 10 what happens, this S4, because S4 it takes 2, so that's why S4 continues of I2 instruction. Now here I2 is completed, 10 clock cycle, I2 in the first iteration it is completed. Now S4 is busy, that's why it has to wait. Next I3 will not enter into S4 at this time. Now S3 is free, that's why I4 enters here, and S2 is free, then I1 enters here. Okay, then S2 is busy, it has to wait, and S1 is free, the I3 in the second iteration enters. Okay. At clock cycle 11 what happens, this S3 completed, I3 will enter into S4 stage and takes continuously 3. See here I3 will take 3 clock cycles. Anyway, so here I4 if you observe after S3 stage it will take 2 clock cycles, that's why it continues S3 and S3. Okay, because S3 is busy, it has to wait. next stage will not enter into S3. Now S2 is free, that's why I2 in the next stage will enter into S2 stage, and S1 it continues I3 because it takes 2 clock cycle S1 and S1. Now at clock cycle 12, right, S4 continues because I3 will take see here, I3 will take 3 S4 3 clock cycles, so S4 continues, and because S4 is busy it has to wait. Now S3 completed, it can enter I1 in the next iteration enters S3, and S2 continues because I2 will take 3 S2 clock cycles. S2 continues, and S2 is busy, it has to wait even though it is completed S1. Then S1 is free, the last instruction in the second iteration it will start S1. Like that in the clock cycle 3, S4 continues here because S4 is busy, it has to wait, and here also it has to wait. S4 is busy, it should not enter. Now S2 continues to 2 clock cycles here according to given data, and here it is stalled because S2 is busy, and it is also stalled. Now clock cycle 14, what happens? The S4 is completed, that's why I4 enters to the S4 stage, and S4 is busy, it has to wait, and S2 completed, S3 is free, it will enter here, and S2 is free, that's why instruction I3 in the second iteration enters to S2. S2 is busy, it has to wait, stall. Clock cycle 15, then S4 is completed here, that is first iteration completed at the 15th clock cycles. First iteration I1, I2, I3, I4 completed. Then because S4 is busy, it has to stall here. Then S3 continues according to the given data, and because S3 is busy, it has to wait, and S2 is free, it will enter, the last instruction enters to S2 stage. Clock cycle 16, now this S4 is free, that's why the first instruction is completed here. S4 is busy, it has to wait, and S3 is free, it will enter into S3 stage, and S2 continues according to the given data. Okay. The clock cycle 17, this S4 stage is free, that's why instruction I2 in the second iteration enters to S4, and S4 is busy, it has to wait, and S3 is free, it will enter and continues to 2 clock cycles. At clock cycle 18, S4, that is I2 in the second iteration completed, S4 is busy, it has to wait, and S3 it continues according to given the data. And clock cycle 19, S4 is free, that's why instruction I3 of second iteration enters to S4 and continues to 3 clock cycle according to the given data, because S4 is busy, it has to wait. And clock cycle 20, S4 continues, and S4 is busy, it has to wait. And clock cycle 21, okay, S4 completes here, I3 instruction I3 in the second iteration completes here, and it has to wait because it is busy. In the same time, it has to, instruction I4 should not enter into S4. Then at clock cycle 22, S4 is free, that's why last instruction in the second iteration enters to S4 and continues to next clock cycle, because according to given data it is taken 2 clock cycle. See here, I4 2 clock cycle, S4 I4 S4 2 clock cycles it will take. Okay, so to execute 2 iteration of the given 4 instructions, it will take 23 clock cycles. That is the answer. B is correct answer. Yeah, observe here, gate 2013 for 2 marks it is given. There is a how many stages given? 5 stages are given. What are they? FI, DI, FO, EI, execute instruction, and WO, right operand. 5 stages are given. Stage delays are given, right? 5 nanoseconds, 7 nanoseconds, 10 nanoseconds, 8 nanoseconds, and 6 nanoseconds respectively for each stage. Okay. time delay. Previously, up to this, what we assume, each stage will take 1 clock cycle. It may be 1 nanosecond or 10 nanosecond, time is not given, but here time is mentioning. Fi will take 5 nanoseconds, Ti will take 7 nanoseconds, Fo will take 10 nanoseconds, like that it is taking. And one more information is given, there is a delay for each stage, that is 1 nanosecond. Between each stage to each stage, 1 nanosecond is given. Now 12 instructions are there, I1 to I12, 12 instructions are there, is executed in this pipeline processor. In that 12 instruction, I4, if you consider, I4 is the only branch instruction, and its branch target is I9. I4 to I9 directly jumps, okay, because that is a branch instruction. If the branch is taken during the execution of this program, the time, that means execution time in nanoseconds needed to compute the program is 132 nanoseconds, 165 nanoseconds, 176 nanoseconds, and 328 nanosecond options are given. So if you observe this problem, how to handle this one? Now there are 5 stages and each stage will take different timings. Now in this problem, the 5 stages are given and each will take different nanoseconds, right? So our assumption is, so previously each stage is 1 clock cycle. So if you observe, a number of instructions are more, for every clock cycle it will give one output. For every clock cycle it will give one output, because all stages are busy, okay. So here also, for every instruction, for every clock cycle, one instruction is executed. There are 12 instructions, okay. So for every one clock cycle, one instruction will be executed, that means, but here the timings is different. We need to take the maximum time. That means for every 10 nanosecond, one instruction is completed. Maximum time for the clock cycle we need to consider. That one point we need to remember. So to execute one instruction, we need to take the maximum time, that is 10 nanosecond plus 1 nanosecond, that is delay between each stage. So for every 10 plus 1, 11 nanosecond, one instruction is executed. That is point we need to remember. Now let us see, because there is a branch instruction. If the branch instruction is not there, then n plus k minus 1, that is n stages, total 12 instructions plus 5 minus 1, that equal to 12 plus 5, 17, minus 1, that is 16 into each one 11 nanoseconds, right? How much? 6, 176 nanoseconds, okay. If branch instruction is not there, this C option is correct, okay. This answer also will be given to confuse. So but because there is a branch instruction is there, let us see what is the correct answer. If there is no branch instruction, then to execute these 12 instructions, how much time it will take? N plus k minus 1, that is n equal to 12 instructions, k equal to 5 stages minus 1, that is 16, into each clock cycle the maximum will take 11 nanoseconds, because this we need to consider 10 plus 1, that is 176. This answer also will be there in the C option, okay, but this is a wrong answer because of there is a branch instruction, okay. So let us see the correct answer. Yeah, the clock cycle time period, each clock, because see here at T6 this instruction will be T7, this instruction completed T8, this instruction, that means for every clock one instruction will comes. So that's why the maximum delay we need to take plus the buffer delay, that means 10 plus 1, that is 11 nanosecond. For each 11 nanosecond one instruction is completed. Yeah, at time T1 clock cycle 1, what happens? I1 enters into IF stage, and T2 clock cycle time, second clock cycle, the I1 enters to DI stage, and at the same time IF is free, so instruction I2 enters into IF stage. At T3 what happens? So I1 enters into F4 stage, okay, and I2 enters, DI is free, that's why DI stage, and at the same time IF is free, that's why I3 enters into IF stage. At time T4, this I1 enters into EA stage, and FO is free, that's why I2 enters into FO stage, and DI is free here, so I3 enters into DI stage. And at the same time IF is free, so this I4 enters into IF stage. At T5 what happens? This I1 enters into W stage. I1 is completed in this time, and at the same time EA is free, that's why I2 enters into EA stage, and FO is free, that's why it enters into FO stage, and DI is free here, it enters, I4 enters into DI stage. At the same time I5, instruction I5, because you don't know, this is the branch instruction, this is the branch instruction is there here, but you don't know the branch where it has to jump. Actually it has to jump to here. The jump instruction should be taken from I4 to this one, but the target address you don't know until it is execution. That's why here what happens, this I5 already enters into the IF stage because IF is free at this time T5, right? Because you don't know until the execution of this W operation, execution unit EI, okay, it's going on entering until this instruction, this execution instruction, you don't know it is the branch instruction, it is a branch instruction and it has to execute to I9, you don't know. That's why the T5 already I5 entered. And T6 what happens? First I1 is completed here, already in the T5, so I2 enters into WO stage, and I3 enters into EA stage, and I4 enters into F4 stage, okay, and I5 is also entered into DI stage because DI is free, you don't know it has to jump to I9, okay, and I6 also, IF is free, I6 also enters because you don't know, right? It is it has to jump to I9 until EA instruction. At T7 what happens? Oh, I2 is also completed in the previous clock cycle, so I3 enters into WO stage, it is free. Now I4 enter into execution unit stage. So until this you don't know, that's why it enters into F4 stage. Okay, operand forwarding is not there, not mentioned, that's why you don't know. That it directly enters into F4 stage, I5, and I6 enters into a DI stage, and I7 also enters into IF stage. At T8 clock cycle, at the execution of the branch instruction is completed, then it knows that these everything is waste of instructions, I5, I6, I7, so it delete that everything, and anyway this enters into WO stage, no problem, but in the IF stage it will not enter into this. I5 will not enter into execution unit because it already know it is a jump instruction, it has to go to I9, so I9 is fetched in this part everything is, it deletes, okay, because until the execution of branch instruction at EA stage, at this T8, until T8 you don't know that this is the branch instruction, it has to jump to I9. So once the execution of this branch instruction is completed at T7, it knows the next instruction should be I9, then directly it fetches into the pipeline, the I9 enters. and at T9 it is entered to, because I4 is already completed, and I9 enters to this DI stage, and continuously IF is free, then it enters into the pipeline stage. I10 enters, and at T10 this this is F4 and this is DI. DI is free, and now IF is free. I11 enters, okay, and the next clock cycle T11, this enters into execution of instruction stage, and it is F4 stage, and this is DI stage, and I12, the last instruction, because 12 instructions are given, this enters into IF stage, and T12, okay, EI, it is WO stage, and it is EA stage, because F4 stage is free, F4, and the sequentially going on in the pipeline DI. At the T3 and T13 clock cycle, this is WO stage, and this is EA stage, and this is F4 stage, and the clock cycle T14, and this is WO, and this is EI, and T15, the last instruction, and this is W stage, right, the operand stage. So all the 12 instructions are completed, right? Because of this branch instruction, this will not continue. I5, I6, I7, those will be deleted, and then I9 enters into the pipeline. So to complete total program, it will take 15 clock cycle. Option B is correct. So observe this, this question asked in GATE 2018 for 2 marks. There is a risk processor is given. Following stages, how many stages? IF, ID, OF, PO, and write back. 5 stages are given. Each IF, ID, OF, WB takes 1 clock cycle for every instruction. There are total how many instructions? 100 instructions are there. And in the PO stage, differently it is executing. 40 instructions take 3 clock cycle, 35 instructions will take 2 clock cycle, and remaining 25 instructions will take 1 clock cycle. So all the 100 instructions will take one clock cycle in all the previous four stages. But in the PO stage, in that 100 instruction, 40 instruction will take 3 clock cycle, 35 instruction will take 2 clock cycles, and 25 instruction will take 1 clock cycle. Assume that there are no data hazards and no control hazards, right? The question is the number of clock cycle required for completion of execution of the sequence of instruction is. Okay, how to deal this problem? Total how many instructions? 100 instructions are there. Okay, so generally total to execute 100 instruction, what is the formula? N plus k minus 1, that equal to n 100 stages 5 minus 1. Okay, this how many? 105, 104. But if you consider all the 5 stages 1 clock, then this is correct. But PO stage some extra clock cycle it will take. That means plus extra how many clock cycles? 40 instructions. Okay, that means 40 instructions. How many clock cycle extra? Actually 1 clock cycle we already calculated. 2 clock cycle extra into 2 plus 35 instruction. How many extra clock cycle it is taking? 35 into how many extra clock cycle? Actually 1 clock cycle we consider. 1 more clock cycle it will take. 2 clock cycle means it is 1 more extra. Plus 25 instruction, only 1 clock cycle, that is already we consider in this. So no need to take that one. So these extra clock cycles are here 2 clock cycles, here 1 clock cycle extra. That means here 3 minus 1, that is the meaning. Here 2 minus 1, because already 1 clock cycle will consider here. 1 clock cycle we consider extra clock cycle 40 into 2, 35 into 1. This is how much? 104 plus 80 plus 35, how much? 104, 80, 35, this is 9, okay, 8 plus 3 is 11, 219, 219 clock cycles. Yeah, 219. See here, the total number of cycles required in general case plus extra clock cycles in the pivot stage. So n plus k minus 1, that is 100 plus 5 minus 1, that is okay. But here 40 instructions, 2 extra clock cycles it is taking, 35 instructions, 1 extra clock cycle it is taking. 20 instruction already that is already taken, 1 minus 1, that is 0 only. So here 104 plus 115, that is 219 cycles it is taking. Let us see the last problem in this concept. Okay, we are discussing the concept, that is instruction pipelining. In that, the first topic, part 1, that is calculating number of clock cycle or execution time, right, to execute the given program. So this question is asked in 2006 for 2 marks. There is a 5-stage pipeline is given, runs at 1 gigahertz frequency. 1 gigahertz frequency means what? Clock cycle equal to 1 clock cycle. How much time it will take? 1 by 1 giga. That is called 1. 1 giga means what? 1 by 1 into 10 power 9. That is 10 power minus 9 seconds. That is 1 nanosecond. That is information. 1 clock cycle is 1 nanosecond is given, right? Now instruction fetch happens in the first stage, that we know already. Conditional branch instruction computes the target address and evaluates the condition in the third stage. Okay, that means a branch instruction previously we have taken up to third stage, you don't know. After third stage, it knows that is a branch address. Okay, that means first 2 cycles will be wasted of the pipeline. The process stops fetching new instructions following the conditional branch until the branch outcome is known. That means until third stage. Okay, you don't know. A program executes how many instructions? 10 power 9 instructions are given, out of which 20% are conditional branches. 20% are conditional branch. Okay, total 10 power 9 instructions, in that 20% are branch instructions are there. That means for every branch instruction 2 clock cycles will be wasted, flushed out. Okay, because you don't know until third stage. If each instruction takes 1 cycle to compute an average, okay, that means each instruction will take 1 clock cycle on an average. The total execution time of the program is 1 second, 1.2 seconds, 1.4 seconds, 1.6 seconds. So let us find out the first for each 1 clock cycle 1 nanosecond, total how many instructions, and he also given 1 clock cycle 1 instruction is executed. So the time execution time takes, okay, to execute 10 power 9 instructions into 10 power 9 instructions into each instruction will execute in 1 nanosecond. That equal to 10 power 9 into 10 power minus 9 seconds. That is 1 second. So to execute 10 power 9 instructions, it will take 1 second. In 1 second, all the program is executed. But in this, extra time is wasted because of this 20% of conditional branches. Okay, 20% of conditional branches. How much time we have to waste? Plus, okay, 20%, 0.2 into, okay, how many clock cycles will be wasted? Up to third stage, you don't know. So first, after completing the third stage, the previous 2 clock cycles will be flushed out. So 2 clock cycle will be wasted for every branch instruction. Now this is 1 plus 0.4, that equal to 1.4 seconds. Okay, option C is correct. Let us see the answer. Okay, one second it will take to execute the program. Please note down by pausing the video, no problem. 20% is branch instructions are there, 2 stalls for every. So 0.2 into 2, that is 0.4 seconds. Therefore, the total time taken to execute the given program is, okay, that is 1 plus 0.4, that is 1.4 seconds. Okay, so please note down this one. So this are about the calculating number of clocks for a given program or execution time for a given program in the instruction pipelining concept. Thank you, friends. In the next video is very important, that is we are going to discuss the speed up and also the throughput, okay, in the instruction pipelining concept. That is also very important. Let us wait for the video, and thank you.